Okay, let's start off with the whole idea of we've talked about how moving charges react to magnetic fields. Question is, where do magnetic fields come from? Now, I talked about that a little bit last time, but we're going to define it, okay? And magnetic fields come from moving charges, okay? So let's just say we have a charge Q, and I'm going to put this at the origin. Charge Q is velocity v times I. Now this means that the vector QV is either in this direction or this direction. VI is in this direction. Okay, so QV so the vector Q times the vector V, which is V times I, right? QV is in the positive X direction. So here's QV. Now the field at the point 0A well, that's what we want to do. We want to find it. In order to find that field, much like we did with two charges, you use an R vector. The R vector from the charge to the point is A times your J vector. Okay. So the field at the point 0A is B you have a proportionality K prime 10 to the -7th magnitude in units, such that you end up with units of magnetic field when you do the rest of this calculation, okay? It's QV cross. And I'm going to write that differently. QV cross I'll write it as R over the magnitude of R. Remind you that that's a unit vector. Okay. Divided by r squared. Okay. So, write out then what that calculation would be if V is D times I and R is A times J. Now we just plug in D times I for V and A times J for R and see what you get. And then tell me what units K prime ought to have. Okay, I'm most people have written it out pretty much like this. Let's factor out the constants. First of all, let's note that the magnitude of A times J. Let's write it down here what I want. Is A times the magnitude of J. What's the magnitude of J? You can just do with your hand. Magnitude of J is 1. It's a unit vector. Okay. So these magnitude of AJ's just become A's. And of course, up here you've got AJ over A, which is just J. This just becomes J. So what you're getting is QV over A squared times I cross J. Now, K prime has nothing to do with the K vector. K prime is just a constant. Notice that this is an inverse square with the distance from here to here. Okay. So just like with a point charge, your field falls off with the distance, okay? As a square of your distance. Now there's a little bit more to it because you have a cross product here. And if you want the field out of a point here, your R vector is no longer a multiple of J. It's going to have an I and a J component, okay? And the distance is going to be greater, and that's going to have an effect that we'll work out in a minute. The cross product of QV and R is out of the board. So your magnetic field is cross product of this and this, so it's out of the board, right? If your charge is moving in this direction, then watch this. If you put your thumb in the direction of the charge, then your fingers, when you get up here, point in this direction, right? Okay. And you could rotate this picture. Your magnetic field would then be circulating around the x-axis, like this. Okay. So there's the direction of your magnetic field surrounding this charge in the plane, in the YZ plane, let's say. Okay, so in this plane, magnetic field does this. There's a symmetry argument to that. Okay. That extends to the idea that if you have a current in this direction, of course, a QV is equivalent to an IL, the current I delta L, okay? If you have a short segment of current, and we'll develop that in a minute, short segment of current along a line in this direction, that short segment will create a magnetic field, again, that surrounds the wire, like so. And we can easily demonstrate that that's the case just by producing a current in a wire and putting a compass over the top of it and under it, okay? It'll be this way and then it'll over and this way under. The compass will deflect in this direction, in this direction. We haven't actually done that. We'll probably do it in lab. Okay. Does that all make sense? You really want to have that picture. Now, if we have a different point, I'm gonna go for that purple chalk. I just wanted a piece of good purple chalk a while ago. I just want a different color. Okay. Let's say that we have a point out here, and let's say that this point has coordinates . Let's call it XA. Okay. Well, this thing produces a field not just here, but it produces one out here. Now, if this thing's moving in this direction, a little later, it'll be producing a field here that's the same as what this field was, right? Because as soon as this thing gets directly under this point, the field's going to be the same as it was at this point. Okay. Which is how, well, we'll get to that. Okay. Now the R vector, well, work it out. What's the R vector and what's this expression? Okay, so I've written out the expression, I think, accurately. You're going to have QV. Your R vector is XI plus YJ. So I think you got that. It's not YJ, it's AJ. If you look, you notice that I had some wet spots here because I wrote down Y's instead of A's, which was unwise. Okay. Yeah, just clever. Okay. Okay. So it comes down to this. You're going to get a magnitude of XI plus AJ cubed. And of course, we know, I think you've written it down, the magnitude of the XI plus AJ vector is just the square root of X squared plus Y squared, right? And I think we've got that. So I'm not going to labor the point. So we're going to get, okay, let's just get all our constants, including the scalar V, QV over X squared plus Y squared to the 3/2 multiplied by I cross XI plus I cross AJ. Okay, I'm going to write it out that way. Of course, I cross I is 0. Move it all down, still visible here. Okay. Make sure all this is still visible. Okay. So okay, this is 0. And this gives you Okay. And one more step. I could have written it all in this step. It's just be methodical. Hey, I keep being a little wise here. Keep writing Y instead of A. That's that in a minute. And I don't want to write this away. Okay. Let's write it correctly. Separate that out. Okay, so it's K prime QV times A over X squared plus A squared to the 3/2 times your K vector. Now we notice that if A is a lot bigger than X, and a lot bigger than X, then this is essentially just 1 over A squared. Because X squared plus A squared, if A is a lot bigger than X, it's pretty close to A squared. A squared to the 3/2 is just A cubed, and A divided by A cubed is A squared. So it's like an inverse square law. Again, if you're close to the perpendicular direction here, that is, if X is much smaller than A, which means your vector here is pretty close to perpendicular. As you get out here away from perpendicular, if X is quite a bit bigger than A, then this becomes like an inverse cube almost, okay? So we'll kind of think about that, but another way of writing this. It's K prime cubed V over X squared plus A squared times A over X squared plus A squared, okay? That's the square root of it. Well, I'll write it all out. I want to be really explicit. I don't want to say too much. Trigonometry, although I think trigonometry is pretty good. Okay. Now, what's the trigonometric meaning of A over the square root of X squared plus A squared geometrically in this picture? We'll talk about that for a minute. So pause. Okay, now we got that, and it took a little while. Okay, so just advice, you really want to make sure your trigonometry is up to speed. Turns out that it's just a sine of the angle between the two vectors. But yeah, it's kind of instructive to see, okay, first thing we noticed was that if you draw a line here, you got a triangle, okay? And you know the 3 sides of the triangle. It took a little while to go around. You can find the angles by arc sines and arc cosines and all that stuff. And the reasoning was a little convoluted because maybe aren't all that used to reasoning in terms of triangles, okay? You really want to be, you really need to be. So kind of make yourself a note, see triangles, okay? What it comes down to though is A, okay, if you're looking at this triangle here, A is this side, right? And this is, square root of X squared plus A squared, magnitude of this vector, and that was seen immediately, okay? So that this angle would have a sine that's equal to this over this. opposite over adjacent. Now you were seeing it in terms of the circular definition, which is equally good. You see the circular definition, you see that well, you would pretty quickly see that if you're looking at the circular model, this right there is the angle that you get from the circular model, okay? Where the y over the r is your sine and the x over r is your cosine, right? Okay, so if you want to look at it that way, well, the y coordinate divided by r is your sine. Well, you immediately see there's your y coordinate, there's your r, so this is the sine of theta. So if this angle's theta, we're going to call it theta now. And we know that that's really good because that's the angle between the two vectors, and that's really the angle we want to focus on. When you're doing a dot product or a cross product, you're looking at the angle between two vectors. And since the two vectors control this calculation, well, that's how we want to see it. Okay, well, anyhow, by making the trigonometric connection, you see this is K prime QV over, I'm going to write now as R squared. Times sine theta times your K vector. Now your book doesn't assume as much familiarity with vector calculations as this class will have, because everybody's been through the logarithmic calculus, okay? And your book just gives you a formula at some point, which is just going to kind of ignore everything except the K prime QV sine theta over R squared. Okay. This shows you that the magnetic field at this point, at points along this line, as you move along here, the magnetic field decreases rapidly. It decreases as an inverse square because of the R squared, but it also decreases, that's an increase and decrease. It decreases, it's an inverse square proportionality. It decreases proportional to the square of your distance here, as well as decreasing because the sine of theta decreases as theta approaches zero. If you move in this direction without changing this distance, okay? So this field falls off very, very rapidly, but it stays significant for a good little ways. I mean, between here and say here, the magnitude of R doesn't change a whole lot. It's still pretty close to A. Okay, and the sine of theta stays pretty close to 1. So for a good little distance here, the field stays almost as big as it is here, but then starts dropping off very, very rapidly. Okay, well, that's worth understanding because ultimately we're going to be talking about charges. Well, soon we're going to be, in a few minutes, we're going to be talking about charges now moving through a current carrier, and we want to get the magnetic field due to that line current, okay? Current through a straight wire. And then we might ask if you've got two straight wires, okay, this wire creates a magnetic field at this position of this wire, and this wire creates a magnetic field at the position of this wire, so they exert forces in each other. Then you got to watch out when you build your power lines, high voltage power. Actually, current power lines carry a lot of current. Okay, and high voltage power lines are high voltage. You can control, you can carry a lot of energy per, a lot of power per unit of current. but you also use big wires, so you can put a whole lot of current through them at very high voltage, so you carry a lot of power. Okay. Okay. Well, let's move on to the magnetic field of the line charge. Okay, just a couple of questions before we moved on. Okay. Again, the question of the right-hand rule for currents. Okay, because this could be a part of a current in a straight wire. Okay, if your point was out here instead of up here, and of course you get that just by rotating your coordinate system. Okay, like this. But your R vector would now be out here. Your QV vector would still be here. So your QV cross R would be like this, so that out here, your field would be down. Well, what does this right-hand rule tell you? It tells you that the field goes around the wire, if you will, in this direction. So that when you've rotated the thing out to here, so your point's now here, well, the field's surrounding the wire in, got my hands are in the wrong direction, but in this direction. So, you know, when you get around to here, it's down. When you get down here, it's in here. And your QV is still here, but your R is down here, so it's going to be yes. Okay. So you want to really reconcile all of that. Because especially if you know, significant portion of the class is looking at electrical engineering, well, duh. Okay, so electromagnetism. Okay. And it's going to be very important too. Okay. Needed the picture to get the camera to focus again. So we'll keep the picture up there for a minute. Has nothing to do with this. No power lines, no wires. Okay. So, well, that picture we had before. Here's the x-axis. Here's the y-axis. Still got to use the 0.08. Okay. But instead of a moving charge, we're going to take a small increment delta L. Okay. If you have a current moving through the increment delta L, then your I delta L is the sum of your QVs, and that's something you hopefully worked out in the last chapter. That's something that's important to understand. What the conduction model, in terms of the conduction model, which I hope you understand, that's what we get. So I'm going to call delta L a vector, multiply that by the current, and you get the sum of all your QVs. So that I got my colors. Yes, okay. Well, this would be like your delta L, but I'm just going to kind of obliterate that. You've got a delta L here, and you've got an I delta L, which acts just like a QV, a sum of QVs. Now, of course, if you have more than one charge moving at more than one velocity, each charge would produce its magnetic field at every point. So the magnetic field at a given point would be the sum of the magnetic fields of all the individual charges. That's superposition. So you want to be sure you understand that. Okay, so, well, again, this is the same picture that we just saw, except we're using I delta L. And we have an R equals AI. and we get our field. Okay, and in this case, okay, so in this case, it's going to be a delta V. So it's the same rule. We've just replaced QV with I delta L. So it's very easy to work out. And I choose to write it this way. Your book is probably going to write something with sine theta in it and so forth. We understand where the sine theta comes from, so you should understand that your book doesn't really do the cross product when it gives you these formulas. And you should really understand it in terms of the cross products since you're familiar with the cross product. Okay, but that's up to your judgment. Now I call this delta V. This is the contribution of this delta L. So I say this is contribution of the current in one delta L increment of your line current. In other words, in one delta L increment of that wire, if you wish. Now we want to discuss for a minute. If we have a length of wire, how do we get the current due to that chunk of wire, okay? Or how do we get the magnetic field due to all the current in the wire, let's say between negative 10 meters and plus 10 meters or whatever, okay? So, or what if we had an infinite line charge? Okay, and it's actually going to be easier to talk about an infinite line charge, which is equivalent to a finite line charge for points that are close enough to that line charge. Because remember, the field contribution of something far away has fallen off as an inverse square and also as the inverse, as the sine of the angle, okay? So it's basically fallen off as an inverse cube. So points far away, much further away than this distance, are going to have angles and distances that make the contribution really small. So you can kind of ignore that, and you can prove you can ignore it just by doing the integrals. Okay. So let's assume an infinite line charge or a much smaller than the length, and you're not close to one of the ends. So okay, I extends for the entire x-axis. What's the field at 0, A? So how are we going to approach this? We know this applies to any increment, any delta L increment, right? So how do you think we're going to approach developing the integral? Okay, now what everybody tends to do here, that's what everybody's tended to do, is you try to figure out what the integral is, and it's all kind of vague, okay? And a lot of it's on the right track. You're looking at the right stuff, but you haven't done the one thing that you always do when you begin to develop an integral. And when I said, what do you do when you begin to develop an integral, I immediately got, well, you partition something. Yeah, okay. Always. What are you partitioning? Okay, so now we want to know what we're going to partition. Okay, now we just had a really good impulse. So, well, you're going to do the current is going to be different from the interval over here than it will from here and all that stuff. So immediately thought of, well, what if you have one at equal distance on this side, two of them at equal distances on these two sides? Wouldn't they cancel out? Well, that's a conjecture that you want to think about the details. So if you got an I delta L on this side, what's the direction of the magnetic field that you get at this point? Well, your R vector is this way, right? And your I delta L vector is this way, so you're going to have this direction. And if you got one over here, your I delta L is in this direction, your R vectors are still. When you turn the I delta L toward the R, you get this direction. So you don't cancel out the reinforced. Okay. Now you might be thinking of what happens with an electric field. Okay. And if you have a charge across here, well, you would get a repulsion or an attraction. Let's say it's repulsion. Okay. So you have a positive charge here and a positive charge here. And so where you get a vector in this direction, repulsion from this one, right? And from this one, you get a vector in this direction. Well, these components reinforce that these components do cancel. Okay, so it's good. I think you were invoking that image. Okay, so I think that was a good attempt. But when you think through the details of it, you're going to find out that, well, this isn't a repulsion. This magnetic field's at right angles to both of these things, so it's not an electric field. And that's one of the essential differences between electric fields and magnetic fields, and their, the way they arise from their sources. Okay, so go on with your thinking though. Okay, without any real prompting from me, we got some pretty good stuff. Okay, so you're going to have to take all your I delta L's and you're going to have your R's for all your I delta L's. You're going to sum them up. Okay, and that's basically what you've been saying, and a few more words, but that's the essence of it, and it's right. I'm going to tell you, you still haven't partitioned anything. Okay, you see what you're going to do once you've partitioned it, and I'm telling you that you just want to write out your partition and then get the expression for the magnetic field for the typical interval. Okay, and then you're going to sum them just like your instinct tells you. So you've got all the right instincts. You're just not doing all the details, but you're this close. Okay, well, maybe this close, but you're getting there. Okay, so let's see if you can get there. Okay, we're kind of spinning around in circles here in this. Okay, so I'm going to give you a big broad hint because we've only got a few minutes left here. Currents along the x-axis. You partition the x-axis. In general, if you can partition a geometric object, that's what you want to partition, okay? Now, sometimes it's more abstract than that, but right now, very clear that the current is on the x-axis and that the partitions that you've been gesturing on are increments of the x-axis, okay? The elements for your partition are increments of the x-axis. Okay, so how do you partition the x-axis? Okay, I'm going to write this out for you because I'm getting time. Okay. Well, just for simplicity, it's a little simpler to partition the positive x-axis because we don't have infinities in both directions. Okay. So to develop the partition of the entire x-axis, that's it. And of course, we can say less than xi. There's no end there. Okay. It's a little trickier to write on a partition of the negative x-axis. Even of the whole x-axis, I'm just going to partition half of the x-axis. And then we'll use a symmetry argument. Okay? And that'll work here. Another way to do this is to just partition the x-axis from negative b to b. Okay? And then let b approach infinity. We partition the positive x-axis, then use symmetry, or and a lot of times we use A here, but I've already used A for the position of the y-axis. Okay. So we do it one of two ways. Typical interval is this. Or typical increment. Okay. And that should be really familiar because we did a lot of that a few months ago. Okay. Then the geometry is simply that you have a delta xi with an xi star. And you have the point 0a. All you need is your R vector. You kind of missed the point, but you get the idea. R sub I, we'll call it the ice R vector, is negative xi star times the I vector plus A times the J vector. In other words, from here to here is 0 minus xi star, right? So this vector's, a vector from here to the origin is just negative xi star. And then vector from here to here is aj. So there's your R vector. Okay. And then I delta L is your I delta L I times your I vector. So that your delta B delta B sub I equals what? Check it out. I don't have room to write it out real coherent. Gee, I thought I had that whole picture on the screen. I've tried to get a monitor and stuff so I could actually see what I'm doing, but I have limited time to nag people. They don't need that much nagging. They're very cooperative, but just nag them a little bit and it happens, but I haven't had that much time. Okay. What's delta BI? K prime times your R vector, R delta L vector crossed with your R vector, right? Well, I was going to have you write that other time. So we have K prime times I delta L cross Ri divided by the magnitude of Ri. All that over the magnitude of Ri. Okay, well, that's written really small, but you should be able to write it out. It's the same thing. We wrote it out before. So you sum all these up, then you let it approach an integral, and it's not a difficult integral. Okay. The direction of every one of these by the right-hand rule, every I delta L is in this direction, right? Okay, and every R sub I is either in this direction or this direction. So you're always going to turn it this way, which is always going to give you vector in the K direction, positive K direction. Okay. And it's I delta L times your I vector. I didn't get that in there. So there it is. It's really small and you can't read it, but it's there. Okay. I'll write it out to you. Delta B sub I. And incidentally, you're going to have to figure out the units of K prime to look it up. The number is 10 to the negative 7th. And it's Tesla per amp meter. I think there's a Tesla meter per amp. But it just comes right out of the formula if you write it out. Okay. And I never remember. I just work it out every time I need it. Okay. Because I remember the rule. That's ingrained. And I don't want any more details in my brain. Okay, I'll develop them when I need them, and then I'll have them at least for a very short term. With my okay, so we have K prime I delta L times your I vector. So I had an arrow over the I delta L, and I'm just going to write it as I delta L times your I vector, put an arrow over the delta L. Okay. The I times direction. I del L times the I vector crossed with Ri divided by the magnitude of Ri, all that over magnitude of Ri squared. And that whole idea needs to get really familiar. There's your source of magnetic field. Another thing I'll mention is the magnetic field to a circular ring of current, which is like the dipole that you get from an electron in an atom, okay? Gives you the magnetic moment and all that stuff. But the magnetic field due to that is much simpler, at least along the axis. Okay, very similar to what you do with an electric field in circular. Right? Okay, and in many ways, a lot of stuff cancels out, and then you get something pretty good. Okay, well, anyhow, that's it for the line charge. Some of the VIs, some of the delta VIs approaches the integral negative infinity to infinity, or from negative B to B in this case. A bunch of stuff. If you take it to the limit, you get something much simpler than what you do if you actually just do the integral over a finite segment of charge. And I'll let you work that out because you certainly have the equipment to do that.